ለመማር ወደ ትምህርት ተቋም መሄድ ግድ አይደለም። ናሽናል አቪዬሽን ኮሌጅ
ራሳችሁን ከኮሮና ቫይረስ ወረርሽኝ እየጠበቃችሁ በቤታችሁ ወይም በተመቻችሁ ቦታ በኢንተርኔት አማካኝነት በኦንላይን ትምህርታችሁን መከታተል ትችላላችሁ።
ካናዳ ከሚገኘው ኢንተርናሽናል ኤር ትራንስፖርት አሶሲዬሽን አያታና ከእንግሊዙ ኢንስቲትዩት ኦፍ ኮመርሻል ማኔጅመንት ICM ጋር በመተባበር የሚሰጡ ትምህርቶችን ተከታትላችሁ በ6 ወር ጊዜ በዓለም አቀፍ ደረጃ ተቀባይነት ያለውን የስልጠና ማስረጃ ባለቤት መሆን ይቻላል።
ልምድ ባላቸው መምህራን እየተማራችሁ ጥያቄና መልስ የክፍል ስራዎች ፈተና መፈተን ክፍል ውስጥ እንዳላችሁት አይነት በኦንላይን ባላችሁበት ቦታ ከናሽናል አቪዬሽን ኮሌጅ
የናሽናል ኤርዌይስ እህት ኩባንያ
Here is the first example. These are the three premises and this one is the conclusion. So after we constructed this truth table, we have to see in which row do the premises have truth value true. The premises are already identified by the stars, so we have 3 stars for the 3 premises. So the 3 columns, the starred columns, have truth value true only in the fourth row. You can see this premise P has truth value true, the second premise truth value true, and the third premise truth value true. So we have got the fourth row in which the premises have only truth value true. So the next step is what is the truth value of the conclusion negation of R. As you know, negation of R is found in the 5th column. So according to the premises truth value, we have identified the 4th row. So the 5th column and the 5th column has truth value true in the 4th row. So you have to circle this one because this truth value is the truth value of the conclusion at which the premises have truth value all true. Therefore, we have got the conclusion truth value is true, and hence the argument, the logical deduction is valid. The logical deduction is valid. So this is the second example, and let's go to the third example. You can use again the truth table for the second example again. So the second example is if the professor offers chocolate, if the professor offers chocolate, if the professor offers chocolate for an answer given, you answer the professor's question. You answer the professor's question. This is the first premise, okay? When you go to the second premise, the professor offers chocolate for an answer. The professor offers chocolate for an answer. Second premise, okay? And the third premise, we don't have any third premise, but the conclusion hereafter is, therefore, you answer the professor's question. Therefore, you answer the professor's question. So you need to identify which one is, or which of the given propositions are premises and which are the conclusion. So let us read it once again. If the professor offers chocolate for an answer, you answer the professor's question. So we have two statements here. Solution. Let P be the professor offers chocolate. The professor offers the professor offers chocolate. First proposition. Second proposition, the second proposition is you answer the professor's question. You answer his question or her question, the professor's question. So do we have any other proposition other than these two statements? Let's see. While we are constructing the argument or the logical deduction, you have to identify whether a given logical connective is applied in constructing the logical deduction, or in each premise and in the conclusion. So the first one, it begins with if. So we have what we call is the implication. So the professor offers chocolate means P. So P implies, then you answer the professor's question. You answer the professor's question is already denoted by Q. So this is the first premise. And then the second premise is, after full stop, we have the professor offers chocolate for an answer. The professor offers chocolate for an answer. So this is P. P as second premise. P implies Q as first premise. Then again, we have therefore. So it is symbolized by this one, and you answer the professor's question. You answer the professor's questions means Q. So Q is the conclusion. So here we suppose the two English statements by P and Q, and then we have constructed the logical deduction. Then we have to go to the truth table. So while we are constructing the truth table, how many number of propositions do we have in this logical argument? Only two. What and what? P and Q. So we have P, then Q. We don't have any negation. So here is P implies Q. P implies Q. For two statements, the number of rows, as you know, are 4. So first, second, third, 4. So here are the 4 rows. So true, false, false for the first proposition, and true, false for second proposition. So in case of implication, we have only one false for the first true and second false. For the rest of them, we have true truth value. True truth value. Now, how many proportions do we have? Only two. What and what? P implies Q, the third column, and P, the first column. So these are the first and the third column are already columns of proportion, but columns of premises. But to identify in which row the definition of premises is already satisfied, so let us see. The premise have always truth value 2. So only the first row, because in the first column, the premise P has truth value 2, and the premise P implies Q has truth value 2. Yet again, we have premise P has truth value 2 in the second, but in the second, P implies Q has no truth value 2. Therefore, we shouldn't take the second row. The same is true for third. The same is true for the fourth. So only first row satisfies the definition of what we call it premise, because premise should have truth value 2. Therefore, in the first row, our conclusion Q has truth value 2. Because our conclusion is Q. Q is the first row, where the premises all have truth value 2, Q has truth value 2. Therefore, the argument is valid. If we have got the conclusion in the first row, the truth value of the conclusion in the first row is false, it will be invalid, okay? It will be invalid. But now, since we have got truth value 2 for the conclusion, hence we are in a position to conclude the argument or the logical deduction given in the first example is valid. So this is the second example concerning the so-called truth table method. Now let us go to the second method, which is formal proof method. The rest of the questions can be done by yourself as a homework. So let us go to second method example. Question number 2 on the slide. On the slide given by 52, the 52 or the 52nd slide. Again, it is given, the example is given by an English statement. Let me read as well as write it. It says, if he studies medicine, if he studies medicine, he will get a good job. He will get a good job. Okay, one premise, because the statement is already closed by full stop. So we have got one premise, and he will get a good wage. I mean, if he gets a good job. Second premise, if he gets a good job, then he will get a good wage. He will get a good wage. Second premise. The third one is the conclusion. It says, therefore, Therefore, he didn't study medicine. He didn't study medicine. Okay. First, let us give letters for each propositions or for each statements. So suppose P has the statement, P will replace the statement, he studies medicine. He studies medicine. Okay. Then Q will supposed to replace or denote the statement given by he will get a good job. He gets a good job. Okay. Do we have any other statement other than these two? He studies medicine. He gets a good job. He gets a good job. He gets again a good wage. So we have one more. He gets a good wage. A good wage. So let us try to construct the logical deduction or the so-called argument. Okay, the statement begins with if, so there is an implication logical operator. So he studies medicine, P implies he will get a good job, Q. Here it is, P implies Q. One premise. Second premise, if he gets a good job, Q, then he will get a good wage, implies R. Therefore, he didn't study medicine. Means negation of P. So here we have P implies Q as one premise, Q implies R as second premise, and negation of P as third premise. So using this logical deduction constructed form, you can able to determine whether this argument is the so-called valid or invalid. So if he studies medicine, he will get a good job. If he gets a good job, he will get a good wage. He didn't get a good wage. There is one missed statement here. He did not get a good wage. He did not get a good wage. So this is the third premise. The third premise was already missed. So he did not get a good wage means negation of R. So how many number of premises do we have? 3. This one as first premise. This one as second premise. Negation of R, he didn't get a good wage, means third premise. And negation of R, P will be the conclusion. So let us determine the validity of this argument without using truth table, but rather using the so-called formal proof method. So let us start from the third premise. Number 1, negation of R is true because it is premise. If something is considered as a premise, we have a guarantee to say its truth value is true. That is what I did in the first in the first reason or in the first step of the logical deduction formal proofing method. So that's what we did. And when we go to the second one, the second step, P implies Q is again true. And third step, Q implies R is already the third step. So both are true because by the same reason that we did or we gave before. Because negation of R, P implies Q, and Q implies R are already premises. Therefore, if they are premise, the truth values are true. Okay? So if negation of R is true, clearly R has false truth value by rule of negation. So R has false truth value. But P implies Q true and Q implies R is true means that P implies R is already true, is true. The reason is syllogism. By step number 2, 3, and principle of syllogism. Principle of syllogism. By principle of syllogism. So we have got P implies R. So here is P implies Q. P implies Q is already true. Q implies R is already true. P implies R is already true by principle of syllogism. And negation of R is clearly true because it's again premise. R is false. So in order P implies R be true and R is already false, so P has, or the truth value of P must be false. If P is true, true implies false couldn't be true. Rather it is false. But P implies R is already known to be true because it is true because of by principle of syllogism and step number 2 and 3. So step number 5, P is false. P is false. If R is known to be false by principle or rule of negation, and by step number 4 again, by principle of syllogism, P implies R is already true. Therefore, to make this implication true, having the second component false, so the first component must be false. If it is true, true implies false, will make it false. That is already against or contradict with that of step number 4. So P is already false. By step numbers 1 and 4. Step number 1 and 4. Step number 1 and 4. So P is false. If P is false, negation of P is true. This is the reason is by step number 5 and rule of negation. But step number 6 indicates that negation of P is a conclusion, and the conclusion is true. Therefore the argument is still valid. The argument is valid. So we have determined or conclude that the argument given by this English statement is valid. So we have got a valid argument once again. So let us add one more example concerning a formal proofing method, and we will proceed to the next step. Okay, so let us add one more. Example number 4. This is example number 3. Now let us go to see example number 4. Let me give you the argument for without an English statement, but symbolically. Example number 4 is given by negation of R and negation of S. Okay. Then again, negation of S implies P, again implies R, The conclusion is negation of P. Negation of P. Let me repeat it again. Negation of R and negation of S will be the first premise. The second premise, as you can see here, is negation of S implies P implies R. Second premise. And the conclusion is negation of P. Okay. Let us determine its validity using 2 premises and 1 conclusion. Using not truth table method, but rather formal proofing method. So let me start from the fact that step number 1 will have negation of R and negation of S is true because it is premise. Number 2, negation of R is true and negation of S is true because by rule of adjunction, Rule of adjunction says that if P and Q is given to be true, therefore the components P and Q will be true. This is one of the rule of inferences. Rules of inferences. So if negation of R and negation of S is known to be true because it is premise, therefore the components negation of R and negation of S will be true. Clearly, R and S are false. By rule of negation, if negation of R and negation of S are known to be true, therefore each R and S will have truth value false. So the truth value of R and S are already known to be false. And let us go to the third step. The third step is negation of S implies P, then again implies R is again true because it is premise. The reason saying this compound proposition is true is its premise. Look, R is known to be false because by step number 2 and by rule of negation, R is already false, known to be false. And this total implication is given to be true because it is premise. So step number 4, negation of S implies P is false. Unless it is false, this implication will not be true or will not have a truth value true. If it is true, that means if it is not false, means it is true. If this one is true, true implies false will not be true. So it will contradict with step number 3. So the only option that the left-hand side component of this implication truth value is false. So this is by step number 2, 3, and rule of implication. Okay. So look, S is known to be false. Negation of S is already known to be what? True. negation of S is known to be true. So if negation of S is true and this implication is false, so P has the only option for P's truth value is false. Because negation of S from step number 2 is true, and this implication is has a truth value false, so true implies false gives us false. So step number 5, P is false. P is false. So if P is false, therefore it will be its negation will be true because the conclusion is negation of P. So P is false. Let us give reason by step number 2. Because step number 2 says negation of S is true. Therefore, step number 2 we have already used that step, and we used which step then? Step number 4. Step number 4 and a rule of implication. Or the so-called modus tollendo opponents. So step number 2, step number 4, and rule of implication. So let us make this conclusion as P, simple P. If it is negation of P, it will be valid because P is false means negation of P is already true. So we have got a valid deduction so many times in the previous examples. Now that's why I already clean the negation part of the conclusion. Therefore, P is false. If P is false, therefore the argument is invalid. The argument is invalid. The argument is invalid. So please make number 4 or example number 4's conclusion without negation. That's why the argument will be invalid. So this is our conclusion. So I think this much is enough for the exercises solutions. So we can go to set theory now. We can go to set theory. Okay. So we have already completed propositional logic. Okay. Propositional logic is already completed. Now we are in a position to start set theory. So in this section, as you can see there, we will study some part of set theory, especially description of sets, Venn diagrams, and operation of sets. So first, before we go to see description of sets or how we are going to describe a set, let us discuss the objectives of this section or the objectives of learning set theory. So after completing this section, you will be able to explain the concept of set. So you should have to explain what a concept of set. So you should have to define a set, and you should have to explain terms or concepts related to set. So this is the first expectation or the first objective. Second, you should have to, or you will be able to describe sets in different ways. Sets in different ways. So this is the second objective. Third, you have to identify operations of sets. Operations of sets. And finally, illustrate sets using Venn diagrams. So explaining concept of sets, describing sets in different ways, identifying operations of sets, and illustrating sets using Venn diagrams are our objectives on set theory. So let us first start explaining the concepts of set. Sorry. So the term set refers to a well-defined collection of objects that share a certain property or certain properties. While we are defining a set, we should have to give attention or focus on the phrase well-defined. The term well-defined here means that the set is described in such a way that one can decide whether or not a given object belongs to the given set or not. So if an object or an element is decided to be, in the given set or not in the given set, so the set is defined well or as well. If we have a doubt or if we cannot able to decide whether or not a given object belongs in the set, so this time the set is not defined as well. So the set or a set must be defined in a well-defined way. So if capital A is a set, then the objects of the collection of A are called the elements or members of the given set A, as you know. So if X is an element of the set A, we write X, then symbol of an element, similarly with that of letter E, as you know. So X is an element of A. If X is not an element of the given set A, we write X, then a bar on the symbol of an element E, the symbol of an element which, as I told you earlier, similar to that of letter E. So you should have to give negation on the symbol of the element. Therefore, it will tell us not an element of the given set A. So as a convention or as an agreement, we use capital letters to denote the names of sets, like capital A to represent set A, capital B to represent set B, and so on. And lowercase for the members of the given set or for the elements of the given set. So uppercase or or capital letters for the sets notation, and lowercase or small letters for the elements of the given set. So this is the convention. So note that for each object's X, and each set capital A, exactly one of X element of A or X not an element of A, but not both must be true. So that's why, as I told you earlier, while we were defining set, an object may be an element of A or may not. So not both at the same time. So this is the notation. Then one has to be aware of, or you should have to be aware of, the concept of distinct elements of a set and how the orders of the elements in the list is immaterial. That means the elements should be distinct. It means that a single element as a single member of a given set should not be repeated more than one time. So that's why the word distinct is very crucial in defining a given set. So a single element must be written once. And moreover, the order of the elements in the list is immaterial. That means we don't care for the order. That means elements A, small b, and small c may come in any order. So if orders of small a, small b, and small c come B, A, C order, it is the same as with that of the order A comes first, B next, and C at last. So the order of the element is immaterial, means that we don't care for the elements. So ABC means the same as with that of the order BAC or CAB or CBA, like that. So this is the first thing that you should be aware of. The second one, let me give you one example. A set should have a brace, an opening brace as well as a closing brace. So one, two, this is example. So this is not a set. Not a set. Why? Because it has an opening brace but has no a closing brace. A closing brace. So this can't be a set. This is the first. Second, one, two. This is also not a set because this opening brace is not closed. This is another brace which is closed for not for this one but for this one. So to make this one a set, we should have to have another closing brace. This time, one is an element. One is, let's say this one is set A. One is an element of set A. And 2 within a brace is an element of set A. But 2 is not an element of set A. 2 without brace is not an element of set A. So in this set, having this brace as opening and closing brace, this one without brace and 2 with brace are considered as elements or members of the given set. So you should have to be careful. Again, I want to add something as an example here. That means we have set B, 2, 3, look. Here it is, opening brace. It is closed here. This opening brace is closed here, and 2 not with its single brace, but this brace is closed here. Now you can see how many number of set B has. You can see 1, 2, or 3, or more than that. You can discuss or you can see, but it has, this set B has only one element. B has only one element, which is 2, 3 in a brace and 1 in double brace, and all 3 are in one brace. So the element of set B is this one. So this set has no 3 elements. Rather, it has only one element. So be careful while describing or defining set. You should have to determine how many number of elements does the given set has, and you should have to list the elements one by one. If it has only one element, you should have to identify which one is the element, and if it has more than one element, you should have to list one by one. So this is the third example. So this is all about the definition of set. The next one is already from the objective that we discussed earlier. We should have to describe sets in different ways. We have said description of sets. So let us start how we are going to describe sets. So the first one is verbal method. Without using brace, we can able to describe a given set verbal. Like the set of counting numbers less than 10. Look, the set of counting numbers, that means the set of natural numbers less than 10. Without using brace, I can able to describe verbal. So the second example is the set of letters in the word Addis Ababa. Of course, we can list one by one and we can use brace, but without using brace, I can able to describe this set verbal by saying the set of letters in the word Addis Ababa. Second example. Thirdly, the set of all countries in Africa. Of course, we can list 55 of the countries which are found in the continent Africa, but without listing them, without using listing partially or completely, I can simply describe this set verbally by saying the set of all countries in Africa. So from the first one, we can understand that a set can be described verbally. Second, we can also describe a set using complete listing method. That means we can describe a given set by listing each element completely. This way of method is also known as roster method or complete listing method. Complete listing method means roster method, okay? So you should have to list the elements of the set or the members of the set one by one, without using dots, 3 dots, or without simply describing verbally. We should have to list each element one by one using roster or listing each element. Example for this, the set of vowels in English alphabet. They are 5 in number. Its elements are A, E, I, O, and U. So we can list the 5 of the vowels of English alphabet letters. Then we have to use brace, so it will be a set. So the set of vowels in English alphabet may be described as opening brace, then letter A, comma, E, then I, then O, then U, then close the closing brace. Example number 2, the set of positive factors of 24. Positive factors of 24 are 1, 2, 3, 4, 6, 8, then 12, then 24. How many positive factors does 24 have? It will have 8 factors. 1, 2, 3, 4, 5, 6, 8, 12, and 24. So we can list each positive factors of 24. So we have already listed each element. So this is the second way of description of set. Then we can go to the third way of description of sets, which is partial listing method. Partial listing method. From the word partial listing method, from the word partial, we can able to understand that we are going to list the elements, but not completely, but partial. In the second way of description, that means in complete listing method, we have to list each element completely, without using commas, dots. Without using dots, we already listed each element completely. But in case of partial listing method, we are going to list some of the elements, then we are going to use dots, especially 3 dots, and finally we may put the last element if the set is finite, and we may not use to describe the last element if the set is infinite. So in the case of the number of elements of a set is too large to list them all, we look for a common property of the elements and describe the set by partially listing the elements. So more precisely, if the common property is simple, that it can easily be identified from a list of the first few elements, then within a pair of braces, we list these few elements followed by exactly 3 dots and possibly by one last element, as I told you earlier. So let's see the examples. The set of all counting numbers, that means the set of all natural numbers. As you know, this set is infinite. So we use opening and closing brace, then we list the first 3 or 4 natural numbers, then we use 3 dots. So this is a set of all counting numbers using partial listing method. Partial listing. The set of non-positive integers. The set of non-positive integers begins with 0, then -1, then -2, -3, -4. It goes like that. We cannot list completely them all. But after we list few of the first elements like 0, -1, -2, -3, and -4, then we use dot towards the left. As usual, there are opening and closing brace. And the third example is the set of multiples of 5. Again, this one is infinite. The set of multiples of 5 goes towards both to the left as well as to the right, because there are negative multiples of 5 as well as positive multiples of 5. So we have 0, comma 5, here is comma, 0, comma 5, so it's, as we did earlier, 0, comma 5, comma -5, -10, -15, then dot goes to the right. And the previous was positive, that means 0, 5, 10, 15 goes to the right. Then -5, -10, -15, then dot towards the left. So this is the third example. The fourth example is, as you know, the set of odd integers less than 100. Odd integers less than 100. Yet again, this one is infinite. So the largest odd integer less than 100 is 99. But since it is integer, we don't know which number is the smallest odd integer. So here we have 99, then dot, then 5, 3, 1, -1, -3, -5, then dot. Towards the right, after 3 dots, we can put 99, because there is no some other less odd integer than 100. The only less integer than 100 odd integer is 99. That's why we have put 99. Towards the left, we let it continue by using 3 dots. 3 dots. So this is how we are going to describe sets partial listing method. So the set which has no element is called, as you know, empty set or null set, and denoted by the symbol as you are very familiar with the symbol of empty set. So the set, example, the set of x, an element of real number such that x squared plus 1 equals 0 is an empty set. I will show, or I will describe it, or I will repeat it once again, this example while we were talking about set builder method. So this is partial listing method. Okay, the fourth description of set is set builder method. That will be the end of this class. So when all the elements satisfy a common property P, or a common property F, or a common property given by some letter other than P and F, we express the situation as an open proposition P of x, or F of x, or G of x, like that, and describe the set using a method called set builder method. This is another method to describe a given set. So you can use this as this one. Look, set A is going to be described with set builder method as follows. Here is x such that P of x, or set A is equal to x such that P of x. If it is F of x. No, how a set is going to be described by a set builder method. So we read it as A is equal to the set of all x such that P of x is true. The set of all x such that this two dots, or what we call it, this brace, I mean not brace but column, this column or two dot will act as, or will read as such that. So the set of all x such that, P of x, an open proposition P of x, is true. Which x makes it true and which x will not make it true depend on the element given under choice. The element given under choice. So this is the fourth description method of a given set. A given set. So of course x may be substituted by t sometimes, or substituted by y, or sometimes it may be substituted by some other letters. So you can have different examples for set builder methods, like set A equals all x such that x is a vowel in English alphabet. If x is A, E, I, O, and U, it will be true. And another example described a set using set builder method. Set B equals the set of all t's such that t is an even integer. All t's, the set of all t such that t is an even integer. This is also a set which is described using set builder method. Or set C given by the set of all n, small n, such that small n is a natural number and 2n minus 15 is negative. So which natural number makes 2n minus 15 negative. So you can insert numbers like 1. When you insert 1 in the place of n, it will be negative 13. So it will be negative. If you insert 2, yet again we can get a negative number, because 2 times 2 is already 4. 4 minus 15 is negative 11. 3, yes, it make it. 4, yes, it can be. 5, yes, it can be. 6, yes, it can be. 7, yes, it can be. But 8 can't be the element. Can't be the element. So a set that can be expressed in set builder method can also be expressed in complete listing method, or the so-called partial listing method. So let me show you this in both set builder method as well as in complete listing method. Complete listing method. Let me show you. So let set C is expressed by the set of all n such that n is a natural number. N is a natural number, and 2n minus 15 is negative. So which n makes this property true? And since n is natural number, 1 can make it true, because 2 times 1 is 2. 2 minus 15 is negative 13, so it becomes negative. And then 2, then 3, then 4, then 5, then 6, then 7. That's all. 7 times 2 is 14. 14 minus 15 is negative 1. So negative 1 is already a negative number. So these are among the natural numbers that makes this property true, being negative. So all these natural number makes this property negative, so that it will be true. So this is a set C expressed or described using set builder method. And this is a set of natural numbers expressed using not in set builder method but in complete listing method, or what we call it roster method, or complete listing method, or roster method. So this is the fourth kind of description of sets. So next time we are going to see operations on relationship between two sets. Relationship between two sets means subsets of two sets, proper subsets of two sets, power subsets of two sets, and so on. So we are going to see a relationship between two sets. After we complete a relationship between two sets, then we'll start operations between sets. For today, this much is enough. Bye bye.
ልዩነት መፍጠር ዓላማችን ነው። ዓለም አቀፍ ተወዳዳሪ መሆን አለባችሁ። የናሽናል ኤርዌይስ እህት ኩባንያ ናሽናል አቪዬሽን ኮሌጅ ጥራትና ደረጃውን የጠበቀ ስልጠና በመስጠት ብቁ ዜጋ ያፈራን ነው። በፍላይት ኦፕሬሽን፣ በበረራ መስተንግዶ፣ በቲኬቲንግና ሪዘርቬሽን፣ በሆቴልና ቱሪዝም ሙያዎች አሰልጥነን ተወዳዳሪ እናደርጉታለን። ኮሌጃችን ካናዳ ከሚገኘው ኢንተርናሽናል ኤር ትራንስፖርት አሶሲዬሽን አያታና ከእንግሊዙ ICM ጋር በመተባበር ዓለም አቀፍ ዕውቅና ያለው ስልጠና እየሰጠ ይገኛል። በፍላይት ኦፕሬሽን በበረራ መስተንግዶ የምንሰጣቸው ስልጠና ከኢትዮጵያ ሲቪል አቪዬሽን ባለስልጣን ሙሉ ዕውቅና አለው። አድራሻ ከጎላጉል ታወር 22 አደባባይ ወደ ሾላ በሚወስደው መንገድ ላይ የናሽናል ኤርዌይስ እህት ኩባንያ ናሽናል አቪዬሽን ኮሌጅ ህልሞን